an exact verification of Kepler's law of ellipses, sorry, an exact demonstration of Kepler's law of ellipses using Newton's laws is a little bit difficult, a little bit beyond this class, a introductory physics-based class, introductory calculus-based physics class. But we will look at it a little qualitatively and see how it might come about. Let's imagine we've got the sun here, and I've got the astronomical symbol for the sun, a circle with a dot in the middle. And let's imagine we've got some planet over here, and at some point in its orbit, let's imagine it's moving up this way. So what's going to happen? Because of Newton's law of gravity, there's going to be a force of attraction acting toward the sun. So there is a force acting on the planet toward the sun. So there's going to be a force in this direction. That will cause, approximately that direction, that will cause an acceleration on the planet, causing the velocity to change in that direction. In other words, if this is the initial velocity, a little while later the velocity will have tipped slightly that way toward the sun. So a little while later the planet might be over here and going that way. Again, an acceleration toward the sun, so that's going to tip the velocity a little bit more, and it's going to make it move over here. And you can just imagine what's going to happen is that it might come around and do something like that. So as the planet moves around, the sun is constantly attracting it toward itself, causing it to accelerate and change its velocity. And you might actually plot this out for a planet. As a matter of fact, this is exactly what I did when I was in high school in my physics course. We plotted out the orbit of Mercury around the sun using Newton's gravitational universal law of gravitation, and or Newton's law of universal gravitation and his laws of motion. And that's actually one of the reasons I went into physics and astronomy, because I just thought that was so amazing that we could plot that out using some very simple mathematical tools. Anyways, so there we go. And what we end up with then basically is the planet orbiting in an ellipse, and the ellipse has two foci and the sun is at one focus. Okay, very qualitative look at the law of ellipses, but that's okay. What I'll do is spend a little bit more time on Kepler's next law, the law of equal areas, and see how that works out. So let's imagine we've got a planet going around the sun here in an ellipse. At some instant in time, imagine the planet is here and it's moving in this direction. So it's at some distance r from the sun. Looks like this. Here's r. Now, what does the law of equal areas state? It states that the line from the sun to the planet sweeps out equal areas in equal times. So let's imagine we wait some time delta t. Now, if this is the velocity, the planet is going to move a distance of v delta t in some time delta t, approximately. And that line then will sweep out this area. So this is the area, delta A, which is supposed to be constant for any amount, delta t. So we look at an amount, delta t over here, we get some area. We look at the same delta t over here. When the planet is closer, what we would have to do is have it actually sweep out a longer distance, because this is shorter than that, and so the area, in order to be the same, this would have to be longer. So if we wait a time delta t over here, we are supposed to get the same area, same delta A for the same delta t. Equal areas in equal times. But let's think about, what is this area? What is the area delta A? What's it equal to? Well, let's think about this. The area, let's imagine that there is some angle here, theta. Okay? The area of that triangle will be the length of the base times the height times 1/2. So the area of the triangle will be 1/2 times the length of the base, which is r, times the height of the triangle. Now if this has a length v delta t, and that's an angle theta, that will be v delta t sine theta. V delta t sine theta. Okay? Now let's just think about this. If we extend this here, that angle theta, this angle would be 180 minus theta. That's what that is. But if we take the sine of 180 minus theta, we get the same as the sine of theta. So we could write this as the sine of 180 minus theta, which I am going to just call phi. So this is the same as the sine of phi. Let's just rewrite this. I'll rewrite this here. Sine phi. Okay, there we go. But let's think about this. What is this? RV sine phi. Well, RV sine phi, that looks a lot like part of the angular momentum. So if we could divide by m, that looks like the definition for the angular momentum. So if we put in an m here and divide by m, this would be r mv, that's p, the linear momentum, sine phi. So that's rp sine phi, that is r cross p divided by m. But what is r cross p? That's the angular momentum. With the 1/2, that is the angular momentum over 2m times delta t. So the area, if we divide by delta t, that rate, delta A over delta t, in other words, the area per time is equal to L over 2m. But let's think about that. What is L? Is the angular momentum, is that changing? Well, we know that the torque is equal to dl dt. So how much torque is acting on the planet? Well, what's causing a torque? Well, there's a force from the sun. The gravitational force from the sun is acting on the planet. Well, is the torque creating a change in the angular momentum? Well, let's look at that torque. The torque is defined as r cross f. So whatever the force is that's acting on an object, we cross r from f. Let's put the origin at the sun. So we'll put the origin here. What is r cross f? Well, what's r? R is the vector from the sun to the planet. What is f? It's the gravitational force, which points from the planet toward the sun. So r and f are in exactly opposite directions. What's the angle between them? If we have r and f, what's the angle between them? It's 180 degrees. What sine of 180? 0. So what is the torque? The torque is 0. Because the force is a radial force, in other words, or a central force, there is no torque on the planet. If there is no torque on the planet, dl dt equals 0, and if dl dt equals 0, what does that tell us about L? It does not change in time. In other words, it's a constant. So this is a constant, which tells us the rate of change of the area per time is constant as the planet goes around the sun, or whatever the object is, whatever this thing is. Could be a satellite, could be a comet, could be whatever. As it goes around the sun, its angular momentum is constant, and so it sweeps out equal areas in equal times. Very, very interesting. Okay, what about Kepler's last law, the harmonic law? Again, to prove that in a general case, that can be a little hard. But we've looked at circular motion, uniform circular motion. Let's take a look at that and see if we can prove the harmonic law in that special case. This is Kepler's third law. Sorry, I forgot to change that 1 to a 2 for the law of equal areas. So in the previous law, that was law number 2. Here we've got a planet, and we're going to look at a special case of the planet going around in a circle around the sun. We know that Newton's second law applies to the planet. We're going to look at F equals ma. Now, in terms of direction, what force is acting on the planet? Well, it's the gravitational attraction, F sub g. What direction is it? It's towards the center of the circle. So we have a centripetal force. So what kind of acceleration do we have? We have a centripetal acceleration. So what we're going to do is we're going to set the centripetal force equal to the mass of the planet times its centripetal acceleration. What's the force? It's the gravitational force, which we know will be g times the mass of the sun times the mass of the planet over the radius of the orbit squared. That's the force, the centripetal force, and that must equal the mass of the planet times its centripetal acceleration. So this equals mass of the planet times the centripetal acceleration, which is v squared over r. V squared over r. Okay, there we go. Now, notice the mass cancels. Now, what is v? V is the velocity or the speed of the planet as it goes around in the circle. So we know that v is equal to the distance traveled in one revolution, that would be 2 pi r, in the amount of time, which would be p, the period. So v is 2 pi r over the period p. So what do we get on this side? R becomes capital R, so we have v squared, which is 4 pi squared r squared over p squared. So that is v squared, and then we divide by r, which gets rid of one of the factors of r. So we have 4 pi squared r p squared. Let's multiply by p squared and divide all of this over there. What do we have? We have p squared equals 4 pi squared over g mass of the sun. R squared times r is r cubed. And what do we get? We get that the period squared is proportional to r, the radius of the orbit, cubed. Well, what was A? A was the semi-major axis. Let me just mention what the semi-major axis means. When we have an elliptical orbit, okay, that's more like an oval and egg-shaped orbit, just something like that, with the sun at one focus. The semi-major axis, the major axis of an ellipse is this length here, the long axis. The minor axis of the ellipse is this length here. The semi-major axis is half of the major axis. In other words, it's this distance here. Now, how does that mean the average distance between the planet and the sun? Well, if we think about this, the farthest the planet is from the sun is this distance here, when it's over here at a point called aphelion. That means the farthest from the sun. So this is the aphelion distance. As opposed to this position over here, which is called the perihelion, which means the closest distance that the planet is to the sun. Well, what's the average of the aphelion and the perihelion? Well, you add these two together, and what do you get? The sum of the aphelion and the perihelion distance is the major axis. Half of that, which would be the average of these two, is the semi-major axis. So this distance is called A, the semi-major axis of the orbit. When a planet is in a circle, it doesn't have two foci. It has, you might think of it as the both foci kind of degenerating to the same point. So the semi-major axis is just the radius of the orbit. And so A just becomes R. And so we have for a circular orbit, p squared equals this thing times r cubed, and that is our constant c. When we put values in for 4 pi squared, g, mass of the sun, we get a constant that turns out to have values of 1 year squared divided by 1 astronomical unit cubed. In other words, when we look at the orbit of the Earth, the time for one orbit of the Earth is 1 year. The semi-major axis of the Earth is 1 astronomical unit. So for the Earth, when we put in 1 astronomical unit cubed, it cancels this. We take the square root, we get 1 year. So because of defining this quantity in terms of the motion of the Earth, we could just write C as 1 year squared per astronomical unit cubed. Which makes it very nice if we want to put in the semi-major axis of some planet in terms of astronomical units, then our period will just turn out to be in years. So we don't have to worry about this value because it's just 1 if we use units of years and astronomical units. All right, very, very good. Let's stick some numbers in here. Let's imagine we're looking at an asteroid that is twice as far from the Sun as the Earth. So here's the Earth orbiting the Sun at an average distance of 1 astronomical unit. Let's imagine we've got an asteroid orbiting the Sun at a distance of 2 astronomical units. And let's figure out how long would it take for the asteroid to go around. Well, what we have is p squared equals c, which is 1 year squared over an astronomical unit cubed, times a, which is 2 astronomical units cubed. So we cube that, and what do we get? We get 2 cubed is 8 astronomical units cubed. That cancels the astronomical units cubed, and we have 8.00 years squared. Take the square root, and we end up with a period that is, whoops, sorry, had this on another piece of paper, 2.83 years. There we go. Very interesting. So, twice the distance, but more than twice the time to go around, 2.83 years. Okay, very, very interesting. This law, the harmonic law, actually works for objects going around other bodies. For example, Galileo looked at the Galilean moons going around Jupiter, and he found something very similar, except the constant is different. When you've got, remember, this constant involved the mass of the Sun, so when you've got objects orbiting around another body, you have a different mass in that denominator from our derivation, but you end up with a very similar result. The period squared is proportional to the semi-major axis cubed, but the constant of proportionality is different. Okay, very, very good. Let's go from looking at the gravitational force in the celestial realm, and let's bring it back down here to the terrestrial realm. What happens when we look at gravity near the Earth's surface?